Hi, this is Nikhil Pembade and this is Rutik, our project teammate. So, I'm going to present my demo presentation. So, here we have implemented the DAC in 3 versions. So, here is the first version as you can see on the screen, and this is the second version, and this is the third version. So, I'm going to walk through the third version. So, here we executed all the 5 tasks using schedule deadline with earliest deadline first and constant bandwidth server. So, by this computation which I highlighted, so why all deadline fixes the schedule. So why all deadline fixes the safety critical and non-critical priority inversion from DAC version 2 under earliest deadline first. The kernel always runs the task whose absolute deadline is earliest. So SC tasks have periods 10 to 50 milliseconds. Non-critical tasks have periods 100 to 200 milliseconds. So safety critical deadlines always arrive sooner than non-critical deadlines. SC task naturally preempt non-critical task without any explicit priority number. The scheduler enforces the correct ordering automatically. So DAC state machine in their DAC state machine in aggressive mode, CPU utilization less than 0.67 and computation factor equal to 0.60. In balanced mode, CPU utilization is 0.67 to 0.87 and computation factor equal to 0.80. In performance mode, CPU utilization greater than 0.87 and computation factor equal to 1. Hysteresis bands prevent rapid state oscillation. CBS headroom equal to 1.205 keeps the total utilization at 0.97 uh, when computation factor equal to 1.0, safely below the single CPU admission control limit of 1.0. So from here, Hutik will take over the demo.
Okay, now we are going to execute our final version, which is DAC version 3. So I'm going to execute this live in our terminal, and which we can see here the compile file has been processed, and now we're going to the second one. So here we make sure, so kernel runtime user is 1, which is in the sudo mode. Okay, that's done, and now I'm going to execute the mid trial on our third version. So as you can see, so we have started the mid trial. So here you can see the warm up is 5 seconds and 30 seconds is the measurement window that we have predefined in our code, and it takes around 30 seconds to completely execute the file, so in which we have predefined all our 5 tasks in safety critical and non-critical tasks. So as you can see, CPU utilization here and the state which is being carried out, balanced, aggressive, and performance mode, and this is our alpha. So we are carrying this experiment now in balanced mode in the mid trial. So as you can see, the state is balanced. So now I'm going to show my results here. So the results have been completely exported into the CSV file, and I'm going to show you the CSV file here. So as you can see, CPU utilization over here, and we have 0 deadline misses in all over, like in all the tasks. So we have scheduled around 13,000 tasks. So in each task we have achieved 0 deadline misses, and this is the response time, finish time, and the task and the job and everything. So now I will walk through the graphs that we have achieved on this. So yeah, so this is the figure 1 DAC runtime. So here this is the mid trial phase. So blue dots here are the 500 milliseconds window measurements. So green step is the DAC, is the alpha DAC selected, and row stays in the in between 0.7 to 0.8 range, which is CPU utilization, and DAC holds balanced throughout. And coming to the third figure over here, this is the vehicle control CV bar. So vehicle control timing jitter across the three trials is 0.03, 0.01, and around 0.075%, at all at least 30 times below the 1% safety threshold. So these all are under the 30 times below the 1% safety threshold that we have declared. And coming to the figure 4, so these all are the histograms. So vehicle before CBS bimodal and CV was 12%. So after CBS, tight around alpha was CV of 0.6%, as you can see. And also in figure 5 and in figure 2, as you can see, we have 0 deadline misses in across all 5 tasks. And I can show you the CSV file just in case. Okay, so this is the CSV file of the all tasks, controls, and that we have measured. So this has around 13,000 jobs that has been done. Oops. Yep, as you can see, the camera processing task, path planning, and everything under the different parameters that we have implemented. And coming to the conclusion, so that concludes the demo. What you have seen is real and is running on the Linux operating system, and it's not in a simulation. So where 5 tasks are scheduled under scheduled deadline, and these are controlled by our dynamic alpha controller. So these are controlled by our DAC supervisor thread in a live feedback loop, and this is the source code, and I have shown you the raw CSV data file. And if you want more information, like more detailed walkthrough, or like what we have did and what are the phases that we have, like what we have learned from version 1, version 2, and version 3. So what all the changes we have did and what are the implementers that we have carried out. So you can see everything in our report, and you can see the detailed analysis of the graphs that I have shown just now. So I have not went through the graphs in more detail, just because I have explained this graphs in detail in the presentation that we have just shown in the PPTs. So yeah, and I just want to show the execution part. So yeah, I think I'm done. Thank you.
Thank you.
Thank you.